Welcome to the guest lecture of the course. Today I have the great pleasure to introduce Tommy Cohn. He's a PhD student at MIT. He works with Professor Russ Tedrick. So today he's going to be talking about bimanual IK, constrained motion planning and analytical inverse kinematics. So this is going to be a great lecture because it kind of connects to the stuff that you guys learned through the course. So he's going to be presenting this work in ICRA, which is one of the top conferences in robotics in next month in Japan. And this paper is already nominated for the best manipulation paper. Is that correct, Tommy?
Yeah.
So I'm super excited to learn what Tommy has done in this space because this is like the cutting edge solution for bimanual manipulation. So let's hear it from Tommy. Thank you.
So I've been getting really interested lately in bimanual manipulation. So I'm specifically thinking of cases where you've got a robot, maybe it's a humanoid, maybe it's just sort of you have two arms on a rolling base or even just on a desk somewhere. And we're thinking about cases where we're holding an object with both hands and sort of a rigid grasp. We see this in a lot of sort of human tasks, like we're picking up a heavy object, whether that's just that it's too heavy for one of the two arms or it gives more stability. Maybe it's that it's like a really large or unwieldy object. Certainly when I'm carrying like a really large box, I'm using both hands for it. We also see this arise in tool use. A lot of tools require both hands to hold the tool at different locations. Or maybe you're providing sort of fixture to the environment. So you're holding an object with one hand and like it's a potato and you're holding a vegetable peeler in the other. And that leads to these sorts of kinematic constraints in task space. And that provides a ton of different challenges for motion planning algorithms. And we've got sort of a new way of thinking about this using some old tricks from analytic inverse kinematics. And it allows us to do some really cool motion planning. Now, oftentimes when we're thinking about planning with constraints, we're really thinking about, we think of it as sort of like a control problem, right? We have some force sensors in the robot, and we're using feedback from those force sensors to try and sort of move the object without damaging it. But really, we really want to see it as a planning problem. We're sort of ahead of time. We say we have these objects, we want to move them. How do we move the arms while keeping the hands perfectly fixed? And really just maintain that constraint as precisely as possible. And the way I see it is if we can do all this in the planning stage, then when we actually run it on the robots, it's a much easier problem for the low-level controllers to follow. And therefore, you can do it a lot faster while still being safe. So we're sort of pulling together two different ideas in robotics. The first one is this idea of constrained planning. In general, how do we do motion planning with these constraints? Just like you would do motion planning with an RRT planner or PRM, as was covered in the class, you have to do things a little differently when you have these types of constraints. The second part, we're going to look at sort of expanding on this idea of analytic inverse kinematics. So as opposed to the iterative optimization methods like the Jacobian transpose or a pseudo inverse, we're looking at sort of by hand or with automated tools generating closed form solutions. And that, it turns out, leads to some very special tricks that really make this problem a lot easier. The way we're actually going to do the planning is we're going to sort of put those two together, and we're going to say, we're going to come up with a new choice of coordinates, a new choice of sort of free variables that we get to pick for planning problems. And it's going to take this constrained problem and turn it into an unconstrained problem. And then we'll show off how you can use any planning algorithm. We try to be compatible with whatever type of planning algorithm you want to use. It will work using this technique. So let's go ahead and dive right in. So for starters, when we think of constrained planning, really the idea is it's just configuration space planning in a harder configuration space. So think about this, you have an arm with two joints, and you're sort of moving around the world, and you have some obstacles in the world. On the left, we have what we call task space. We can see this is where, this is the real world. But we always do our planning in configuration space, where we consider the two joint angles that the arm is making. And these obstacles that you can see are sort of weirdly distorted, and sometimes they're broken up into different pieces and changing shapes. And usually we can't come up with exact closed form descriptions of what those obstacles look like. So we have to rely on other techniques. With sampling-based planning, with the RRT planner or the PRM planner, we're relying on the fact that although we can't construct the obstacles explicitly, if you give me a point in configuration space, I can check whether or not it's in collision. And that ends up being a really powerful strategy because we can draw tons of samples from the space, and we can link them up into a graph or a roadmap or some other structure. So even though we've never actually explicitly constructed the obstacles, we can still plan and we can still avoid them. But when we start throwing constraints into the mix, things get a little bit harder. So I want to think about this specific example where we have a robot arm, and it has, it's just living in the plane, and it has 3 joints. But we're now adding the constraint that its end effector has to be along this vertical black line. So if you randomly pick a configuration, it's probably not going to be the case that the end effector is somewhere on that line. And if you actually sort of densely sample the entire world and project your sample somehow, the actual set of constraint satisfying configurations is this 2-dimensional strange surface in the full 3-dimensional configuration space. And the challenge there is because it's like a surface in 3D, if you draw a sample from the 3D space, the probability that the sample is actually on that surface is 0. There's always going to be some small amount of numerical error, or even potentially a large amount of numerical error. We don't have a way of constructing that surface in closed form. So for sampling-based planning to work, we need some way to draw samples from that. And throughout the lecture, I'll stop for questions, and I want to just stop here and make sure that this sort of picture makes sense. So we have this. Is there a question? Sorry.
No, I think people are saying thumbs up.
Okay, awesome. Yeah, I can't see you guys, sorry, but that's great. So the main question, at least in sampling-based planning, which is sort of the most general approach, is how do we draw samples from a space like this? People have been studying this problem for decades. There's a lot of techniques out there. I want to look at sort of 2 of the mainstream techniques that are used a lot these days. So the first is this idea of doing numerical projections. So what I'm going to say is I'm going to draw a sample from the configuration space, and then I'm going to do some numerical procedure to try and move it closer and closer to that constraint surface until eventually I get close enough that the numerical errors are insignificant. And that's generally a pretty reliable strategy, but you end up having to sort of tune these numerical algorithms. The other approach that people have used and that I think is really popular today is you can try and build up an approximation of the space with like a bunch of piecewise linear pieces. So like imagine like you have a surface and you're trying to fit like little flat pieces together, forming like a mesh of the space. And people have used both of these techniques. They're very general, right? They work for any type of constraint. So just to go into a bit more detail, for the numerical projection algorithm, if you think back to your Jacobian pseudo-inverse or your Jacobian transpose algorithms, those were numerical algorithms where you look at what your current position, you look at where you are currently, and you try to minimize the error. So you might do gradient descent. There's other techniques such as Newton's method that can sometimes perform better. But if you've done numerical optimization before, you've probably dealt with local minima before. And what we usually observe in these cases is that if your sample is very close to the manifold of constraint satisfying configurations, the projection step will probably work pretty well and it'll be pretty reliable. But if you're really far away from it, it's very easy to get stuck in a local minimum. And that's generally a problem because most of the samples you draw, you're going to run this numerical algorithm for a while, only to find that it didn't actually succeed and you don't even get a valid sample from it. And there's tons of parameters you can tune for these numerical algorithms, but you're going to spend a lot of time tweaking your hyperparameters trying to get it to work. As for the piecewise linear approximation, these approaches are actually a lot more robust. So right here, this is just sort of an animation of how these algorithms work. What you do is you pick a point that is constraint satisfying. You just need one. And then it tries to sort of build up this mesh approximation of the whole surface. and it's emanating outwards and so on. So normally when you would run these algorithms, you would have two stages. The first stage is where you build up this approximation, and that takes a long time, and it's somewhat inefficient, but it's very reliable. And you would run this until it completes, until it says, I've described the whole constraint surface. And then once you've done that, then when you draw samples, what you do is you just pick a piece, and each piece is just like a little linear patch. And then you pick a random spot within that linear patch. So in that way, you're always able to reliably draw samples from the constraint manifold. And you can oh, go ahead. Yes.
So I just have a question that, so you have to do some sort of like offline processing to build up to a particular task for doing this?
Right. That's the downside of these approaches. For the projection algorithm, for example, that is used a lot with like a probabilistic roadmap, where you would be drawing tons and tons of samples offline to build your roadmap. But it doesn't work as well, I think, with like the one-time planning RRT approaches, because most of the samples won't be useful. As for these numerical continuation approaches where you build up that mesh, it's going to take a while to construct it, and it's not really useful for online planning.
Got it.
Now, there are ways to sort of interweave these continuation approaches with an RRT, where you can imagine sort of like when you do the extend step of RRT, if you hit the boundary of the piece you're in, you move to the adjacent piece of the mesh. And if there is no adjacent piece of the mesh, you try to construct the next step. These approaches are a little bit better because in practice, you don't actually have to construct a super detailed mesh of the entire thing. You're able to just sort of greedily explore only the parts that you care about. But speaking from personal experience, when working on this project, these algorithms are really frustrating to tune. You have to spend a lot of time. You really have to hold their hands along the way. So they always work, but whether it takes you a few seconds or a few hours is just like a slight change in the numerical parameters. So there's one other cool trick that's sort of, you can take the problem away from planning and look at having really good control, or just having like soft robots, right? Like if you imagine if your robot has like soft hands and you're holding an object in both hands, then you don't actually have to plan perfectly, right? Because sort of the hands will stretch or deform a little bit to deal with the constraint violations. And people have even written controllers that are sort of doing very careful force feedback, where if one arm moves a little too far, the other arm has a controller that's going to try to minimize the forces it's feeling and try to balance it out. And these approaches are nice because they can really elegantly blend the planning problem and the control problem into a single manipulation pipeline. But I think the downside is that the more constraint violations you have to deal with, the slower and the more carefully that you have to move. And I really want to move robots as fast as possible. I want to take them to their hardware limits. And in that case, like it would be very easy to break things if you weren't being extremely careful. So this is a good option, maybe if you're around people or something, but probably not for assembly lines where you want to be very, very fast, very precise. So this is sort of what the world of constrained motion planning looks like today. And obviously there's other techniques for it, but these are sort of the mainstream algorithms. And I know in one of the early lectures, Karthik mentioned the Open Motion Planning Library, OMPL. OMPL implements all of these algorithms, so you can try them out for yourself quite easily. And it's a very nice implementation. So if you ever want to do a project involving this, you don't have to implement these numerical algorithms from scratch. There's excellent library support. All right, so the next part I want to move on to is going into analytic inverse kinematics, but I want to stop here for questions about sort of the existing approaches to these problems.
Any questions? Nope.
All right. So let's move on and let's start talking about analytic inverse kinematics. So when I was sort of first taking an undergrad robotics class, and I was first sort of learning how robotics worked. The only kinematics I really learned about were the iterative algorithms. So I've stolen these slides from one of your earlier lectures, which I think were in turn borrowed from a class at Michigan. But I really want to focus on this bit here in the bottom left, where we look at the IK procedure. So we have what our current X are, we compute the error between the end effector's current position and its desired position. Then we use the inverse of the robot's Jacobian to compute a direction to take a small step. And then we take a small step along that direction in order to bring the end effector pose to be a bit closer to its goal. And this is sort of a classic iterative algorithm, right? We take a small step, we get a little better, and we do this over and over and over until eventually we converge. And there's this in particular is the Jacobian pseudo inverse, but there's a lot of others. You learned about Jacobian transpose. There's these algorithms are really general, and they just work really well. I've never had problems with them. Right, where you can see you're going one step or not, one step at a time, just incrementally getting to where you want to be. Another cool algorithm I've seen for numerical approaches to IK is a cyclic coordinate descent. This is like sort of a much more what's the word? This is like a sort of, I almost want to say like a much more primitive algorithm, but it works really well, where you're just sort of, you're going one corner, one joint at a time, trying to get as close as possible to the goal. And you just keep doing this step by step, and it gets really, really close, and eventually it just converges right to the goal. So, there's that. There's also other approaches. If anyone's familiar with like formal optimization theory, there's techniques to do sort of like, very complicated optimization formulations where you write out the problem and costs and constraints, and you feed it to the computer, and some expensive commercial solver does everything for you. But the main thing I want to emphasize here is that all of these algorithms are iterative. Right? You're relying on a numerical procedure to get you to the goal. But if you need it to be as fast as possible, there's another way. And I know that this was discussed a little bit. This is analytic inverse kinematics, where we want to write out the closed form solutions. So if you think about an arm with two joints, if I want to put the end effector to a certain configuration, I could draw out a couple of triangles and write out the angles, rather like in this picture, and probably come up with the equations by hand pretty quickly, where you determine the end effector pose in terms of theta 1 and theta 2, and then you just switch the equations around. I think most of us, I think probably all of us here with a little time, and if we felt motivated to, could come up with those equations pretty quickly. But robot arms are generally more complicated than two joints in the plane. Maybe a more illustrative example would be like if you have three joints and you also care about the orientation of the end effector. This is still tractable to come up with by hand, but you're definitely starting to make things a little bit more complicated. And as we go to robot arms in the real world, you might have an arm with 6 joints or 7 joints. Then it starts to become a lot more complicated. And we can't always come up with solutions. But there are some classes of robot arms that have like really, really elegant tricks that people have come up with. So my favorite example is if you have a 6-DOF arm. So you have a robot with 6 revolute joints. You can group the first 3 joints together, and you can pretend that they're like the shoulder on the human body. And you can group the last 3 joints together and pretend that they're like the wrist on the human body. And if you think about, your body, you have a spherical shoulder joint, and your wrist also sort of functions like a spherical joint, right? You can move it sort of up and down, you can rotate it, you can turn it left and right. You have a pretty limited range of motion in that direction. So the idea is that you're going to sort of group the revolute joints together in such a way, and you're going to call them a shoulder joint. And this is sort of like, if you think about 6 degree of freedom pose, we can represent orientations using roll, pitch, yaw. And in this case, we can, as long as the axes of the revolute joints all intersect at a common point, it turns out that you can treat all 3 of these joints as if they were a spherical joint. And then at the end, once you've figured out what the state of the spherical joint could be, then you just have to derive from there what each of the individual revolute joints should be. And then a similar process can also be done with the wrist. So this is like a really elegant solution. I think a lot of robotics textbooks, if you sit down and actually read them, will, which I haven't done admittedly, will actually go through a derivation of this by hand. And it's an interesting exercise to do at least once. And there are papers out there that have done similar things. But I want to stop briefly for questions. Does this idea make sense where you sort of group the joints together and pretend that they're a single spherical joint?
Yep, there are a lot of nods. I think there is a question, Matt.
So if you group like a separated group, what's the definition of the the blue circle and the red circle? Like, is there like do you consider there's a ground or or how do you define that space?
So I think the question is more towards the definitions of this blue circle and red circle. And if there is a notion of ground, like a common frame of reference.
So inevitably with these things, it's, URDFs are not sort of unique. There's many different ways to write the kinematics of a single robot. So certainly if you chose coordinate systems for each of the links and each of the joints, you could choose them in a easier way or a harder way. Usually people will talk about other parameter systems to describe robots like Denevit-Hartenberg, which uses fewer parameters. Let's see. I think in these cases, there's always a way to write the kinematics down to make things as simple as possible. But usually that's up to sort of, whatever you're being given. I'm sorry, I don't know if that exactly answered the question.
I think we can move on. Yeah.
Okay. Cool. So now coming up with these solutions yourself can be sort of a frustrating task. But fortunately, we usually don't have to, because other people have done it for us. People have sat down and derived the analytic inverse kinematics for like pretty much all of the very popular arms that people use today. This here is the Kuka Iwa. It has 7 degrees of freedom. It's a very popular robot arm that a lot of researchers use. It's the ones that we use in my lab. Another line is the universal robotics arms. I believe Karthik has a couple of those. There's a paper out there that nicely derives the IK solutions for these arms. Another platform you might have heard of is the Franca Amica Panda arm. This one's also very popular, especially in research labs. Maybe like an older arm, they kind of more or less look the same, but even like arms with much stranger kinematics have solutions, like the Barrett whole arm manipulator. This one is sort of shaped much more differently, but someone still sat down and they figured out all the equations. So when I'm actually sitting down and like trying to implement one of these, I basically I make a cup of tea, I print out a copy of the paper, I go through all their equations, and I just very carefully transcribe them into Python. And then I write a couple tests to make sure I did it right. But it's usually you don't have to come up with these yourself. You can use what other people have already made for you. But there's actually an even better way to do this. There's a really cool tool out there called IKFast, where you just give it a URDF of your robot, and it automatically constructs an analytic IK solution. With a couple of caveats. The first is that it might take a very long time because it's effectively the computer is trying to solve a really hard math problem. It might not succeed. There are cases where it fails. But by and large, this is like a really, really valuable tool you can use. So in some sense, whatever robot arms we have in the future, just because someone might not have made a solution yet doesn't mean you have to. You can just plug it into this tool. And excuse me, once again, this is available online as part of something called the OpenRave framework. But I want to look at something in particular that arises when we really just sit down and think about kinematics for a while. I want to think about this idea of kinematic redundancy. So you've already seen that there can be multiple solutions to the IK problem, right? Everyone always talks about there's the up elbow and down elbow configuration, where sort of you can get your hand to the same place while putting your elbow in different poses. And this is, there's these discrete solutions where like you could have either gone up or down. But when you have more than 6 degrees of freedom on your arm, the picture gets a little stranger, because when we fix the pose of the end effector, that's like 6 degrees of freedom that we're restricting. But if you have a 7th degree of freedom, you can do this really cool thing called self-motion, where you basically keep the end effector fixed and you smoothly move the arm. So this isn't like the arm has to just teleport between 2 opposing configurations. This is a whole degree of freedom you can move along. And this is actually sort of our secret sauce in this, because when we think about the bimanual problem, that self-motion gives us an extra degree of freedom to like avoid obstacles. Before we get into talking about this idea of the parameterization and how we do bimanual planning, I want to stop again for questions.
Questions? There is a question here.
When does IK fast fail?
When does IK fast fail?
Okay, so there's a short answer and a long answer. The short answer is that the order that it chooses to do these computations, like if you think about it tries to compute one joint, then the next joint, then the next joint, that order can dramatically affect how complicated the calculations be. It's like if I go back to the sphere revolute sphere, imagine if I had instead grouped the joints differently. I could have made the problem much, much more complicated. And it can even sort of get stuck altogether. So first of all, if you ever have an example where IK fast fails, they request that you send it to them so they can improve their system, which is very kind. I think the more complicated answer is there's a cool transformation you can do where you can actually get rid of all of the cosines and sines that appear in kinematics, and you only end up with polynomials. And as we know, if you have a quadratic polynomial, you can find the roots with a quadratic formula. But there's not, as the degree of your polynomials gets higher and higher, there's no guarantee that there will be a solution. The solution is there, but there's no like closed form formula to get it. You have to use like a numerical procedure to find the roots of a polynomial. And unfortunately, because of that fact, there are going to be some instances where it just cannot come up with a solution. But I don't know of any instances off the top of my head. I just know it's a possibility.
Cool. Thanks.
But yeah, there's also very cool stuff you can do. Like one way to solve IK in generality is like you can write it as a polynomial, and then you can find the roots of the polynomial using like, algorithms you would use in like numerical computations. And I think people don't do this as often because optimization-based IK and Jacobian transpose just works so well. But it's sort of a neat trick that you can do. It sort of tells you some things about kinematics. Yeah.
There is one more.
Yeah, go ahead.
When you're talking about like that extra range of motion that an arm could have while keeping its end effector at the same position, how does that extra range of motion relate to the previous slides where we saw there was like a dominant and then a subordinate arm? Is that extra range of motion available to both or just the subordinate arm?
That's a very good question. I'll get to that in about 2 slides when I actually show off the controlled and the subordinate arm and like what they're actually doing in these bimanual tasks. But yeah, you're absolutely thinking down the right lines. We're going to be using it. Okay, so why don't I jump back ahead and get into that part. So let's go back to our example where we had a 3-DOF robot with that constraint that the end effector is on that vertical line. When we look at the constraint manifold, right now we can just talk about it as, oh, I have a black box tool that if I give it a value for J1, J2, and J3, it will tell me yes or no I'm on the manifold. But what if instead I had a different algorithm where I gave it x1 and x2, and it mapped those 2 values onto the constraint manifold in some way that we could use? So this is what we would call a parameterization, where we are giving sort of a set of new parameters such that whatever value those parameters take, it'll map onto that manifold. And that's actually really powerful because, with those two parameters, any of those values will work. So we're effectively taking this constrained problem and making it look like an unconstrained problem. So as for how that works with bimanual manipulation and with inverse kinematics, this is where the controlled arm and subordinate arm appear. So actually, I'm going to skip one slide ahead first, and then we'll come back to this. So let's just look at the degrees of freedom in parameterization. I'm going to highlight each joint individually as it's getting moved. This arm here on the left is the controlled arm, and we're allowed to move any of its joints freely. And the analytic IK mapping is going to force the subordinate arm to follow it to keep the end effector pose matched. So in this case, this is all done sort of on the planning side. But remember, we have that extra degree of freedom. We have this idea of self-motion. So this is what our parameterization looks like. This is what our parameterization looks like, right? We have 7 degrees of freedom on the controlled arm, right? Any of those joints can be moved directly. And then the 8th degree of freedom, the extra one that we're controlling, is that self-motion. And this is great because you can move, as you're making your plans in configuration space, the self-motion lets you move the subordinate arm out of the way of obstacles. It helps you ensure that you're satisfying the joint limits on that arm as well. So that's like really, really, really helpful when we're doing planning. It's a whole extra degree of freedom we can take advantage of. So we have this sort of picture of, I think of it as like we're controlling one arm and the other arm is following. But really what we're doing is we're making a plan ahead of time. And we're saying that we are going to make a plan such that the subordinate arm will be able to follow. Does that make sense?
Yep.
So I can actually show you sort of a cool interactive visualization here of what this actually looks like when you're controlling the controlled arm. This is an interactive visualization tool that we use. So you can see here, this arm here, can you see my cursor?
Yes.
So this arm here is the controlled arm, and I can move each of its joints individually. Right, so I can sort of, and as I move it, the subordinate arm, which is this arm on the right, is going to follow it along. And then in addition, we have, this is the self-motion parameter, where I can slide this, and you can see that it's moving that arm, the subordinate arm, but the hands are still fixed. They're still matching each other. You can imagine if there's an obstacle as we're moving around, we can move that to follow. And I think this also gives some cool insights for like what happens when we go to like a non-reachable configuration. And so what ends up happening is like if I push the EWA to the point that it's like out of range, you'll see the subordinate arm, it's going to keep following, it keeps following, it's going as far as it can. Then at some point, it's no longer able to match that transformation, right? This configuration, it's just not reachable, right? And in those cases, we can actually identify that this is happening because if we, we sort of after the fact, we check, did we actually satisfy the configuration? Did we actually satisfy that constraint? And inevitably, as you start going really far in one direction, you'll hit a point like this. So what we do is we pretend there are obstacles. We treat it as like a virtual obstacle. So just like when you draw your sample, you check, is it in collision or not? You also would check here, are the arms reachable? And then one last thing to look out for is you have to worry about the joint limits on the subordinate arm as well. Because with the controlled arm, obviously, we just draw a sample and make sure that it's within the joint limits, right? We say, theta 1 has to be between minus pi over 2 and pi over 2. That's easy. But you can imagine a configuration where we're basically insisting that the subordinate arm violate its joint limits. So like here, for example, you can see that like this joint is getting way too narrow. And you can, oops, sorry, that's the table on the way. You can see that we're going beyond the limits of the hardware. It's actually self-colliding right now. So we treat those as obstacles as well. And what it comes down to is we now have a problem that was constrained, and suddenly now it's not. Now we just have 8 degrees of freedom, and there's no equality constraints. If you draw a sample, sure, it might be in collision, but the probability that the sample is valid is non-zero, right? It's just how complicated is your environment. And really, that's all you need to be able to do planning. You just need to be able to draw samples that are valid, and you need a way to connect them up. So how do people feel about this? Does anyone have any questions?
So just to clarify, so how many degrees of freedom does KUKA have? One KUKA arm?
So one KUKA arm has 7 degrees of freedom.
So the subordinate arm, we're talking about 8 degrees of freedom, but as in the configuration space?
Yeah, so we have 8 degrees of freedom here. So with 2 arms, it's 14 degrees of freedom. You put a 6-dimensional constraint, and nominally you'll have 8 degrees of freedom. If I don't know, have you covered anything about like kinematic singularities in class? Have you brought that up?
No, not really.
Okay, yeah, there's some edge cases where you get like to the boundary of how far one of the arms can reach where you lose a degree of freedom. We avoid those. We just we pretend they don't exist.
Got it.
They're a whole other question. But yeah, so a very good rule of thumb that'll get you far is however many degrees of freedom you are, subtract how many independent constraints you have, and that's how many sort of latent degrees of freedom there are in your problem.
There is one other question.
Yeah.
So in the examples you're showing us, we have both of the n effectors lined up nicely. Is that something that happens within our like analytic IK, or is that something that needs to be manually set up before any of the analytic IK happens?
Oh, I see. So I'm predefining this transform in the sense of like, if I have an object, I'm going to use IK to sample where I'm going to grasp the object with both hands. And then I would do like an unconstrained motion just with an RRT or whatever tool to get the hands there. But then once I close the grippers on the object, then I have to satisfy that constraint at all times. But I can sort of define the transform between them to be whatever I want. Like, actually, I can do that right now. So, for example, like I could make it so they were offset a little bit or something, right? So now so now you can see that like maybe it's holding like an S-shaped object or something. Right? Does that make sense?
Yep.
Cool. All right. I'll shut that down. All right, back to the slides. So so now that we have this parameterization, it's really nice because we've turned our constrained problem into an unconstrained problem. And now you can use whatever planning algorithm you want. So if you wanted to use an RRT, it's easy. You just draw your samples from the configuration space. Sorry, just give this a moment to load. There we go. So this is what like an RRT planner looks like. And you can see it sort of does a little bit of the RRT dance where it doesn't necessarily pick the shortest path. But I want to say again that as we're doing this, it's always maintaining that constraint, right? You know, the hands are always perfectly matching each other as we're moving along, which is really nice. A common point of comparison is to sorry, one second. My apologies. There we go. So if you compare this to sort of like a what we would call a baseline approach, like one of these atlas methods, there's a huge difference in runtime. Like that's an immediate thing. But watch the hands. Watch what it's coming up with. Notice how they're sort of jittering a little bit as it's going on. You know, there's these imperfections in the plan. And this is just due to the numerical tolerance errors, right? So you can see that they're not sort of perfectly mirroring each other, right? Like right here, you can see, you know, moments where it's like see how far apart they are there. And you have to spend a lot of time tuning all the parameters, getting these to sort of match perfectly. And sure, if you have a really good low-level controller that's, you know, able to sort of regulate the internal forces between the arms, you can probably still deal with this, but you're going to have to move slower. There's a whole other side to motion planning. I could give a whole lecture or multiple on trajectory optimization, where just like you can use optimization or like a numerical method to find an IK solution, you can also use it to do all of the motion planning. And that's actually another example. This is like a whole other way of doing motion planning. Just give sorry, takes a moment for all the meshes to load in. And this way you can make like these smooth trajectories that look really nice using the parameterization. But because it's an optimization problem, you could have also just imposed the constraints directly and said, hey, you know, these are constraints you have to satisfy while you're doing gradient descent. Turns out that's really hard. I spent several days just tuning the initialization and all of the parameters associated, and we got it more or less as good as we could get it. But like, if you watch the hands, you'll see that it has these constraint violations. Also, it hits obstacles. That's the other thing. If you use trajectory optimizers, you'll see this a lot. Like, see the hands, you know, it's just, it doesn't quite get it, which is really too bad. But when you compare that back here with like the, you know, when you use this parameterization technique, it's like the algorithm doesn't have to worry about the constraints. And that's really special because it can focus on avoiding collisions and just being, you know, it doesn't have to think about matching the hands. All right, so I think this is, you know, pretty cool. I think I'm always really happy with, you know, how well these algorithms do. I'm curious if anyone has any questions before I move on.
So just for clarification, so what are the methods that you actually compared with right now?
So for sampling-based planning, the planner with the parameterization was an RRT.
Okay.
And the method we compared with was the one from earlier, where you're building the piecewise linear approximation and growing the RRT at the same time. The method is called Atlas RRT. And that's sort of the, that style of algorithm is the current state of the art. There are other implementations that are potentially better. There's, you know, there's versions that are sort of much faster and more precise because they're like written by much more professional software engineers. But yeah, I mean, realistically, you're going to spend a lot of time tuning your numerical parameters with those algorithms.
Okay.
As for the trajectory optimizers, we're you know, there's a ton of different approaches out there. We're using a tool called Kinematic trajectory optimization that's implemented in a robotics modeling framework called Drake.
Mm-hmm.
And we're using it for both of these. So in this one right here, what we're doing is we're not using the parameterization. We're just encoding an extra constraint to keep the hands matched at every time step. And then with the parameterization, we aren't worrying about that.
Got it.
Are there any other questions?
No.
All right. So I always think of sort of sampling-based planning and trajectory optimization as like the two main paradigms in motion planning. Like anytime you see a robot moving and it's not like sort of a reactive policy, like anytime it's sort of, it thinks for a bit, it makes a plan, it runs the plan. It's one of those two. But recently we're starting to see the boundary between them starting to blur a little bit. And there's a new approach that some people in my lab have been working on that I think sort of gets the best of both worlds with these approaches, which is pretty cool. They call it graph of convex sets. And with this picture here on the left, imagine that red, you know, pentagon is an obstacle, and you want to get from Q0 in the top left to QT in the bottom right. When we think about motion planning, at least when it's just collision-free motion planning, there's really two questions. There's the high-level question of, there's an obstacle here. Do I go left or do I go right? But then there's also the low-level question of, what is the exact path I'm going to take? And graph of convex sets is sort of a nice way of reasoning about both of those questions simultaneously. The idea is you're going to break up your configuration space into a bunch of these pieces, Q1, Q2, Q3, Q4, Q5. And then you're simultaneously going to decide which set do I move through and what trajectory do I take through that set. And our lab's been doing a lot of work on this framework. Turns out it's a very general picture, but it's really cool because you can sort of, if you're on like an assembly line or you're in a warehouse, you can build these really, really precise and detailed representations of what the world looks like. And then you don't have to worry about collision avoidance anymore. As long as you're within a safe set, you don't have to worry about it. And we're, just like we can do any kind of planning with this parameterization, we can also use this new motion planning framework. And that was the video that I was showing you at the beginning of this lecture, where we're doing these sort of very smooth and precise motions. And this is fun. We're not actually doing perception here. We've just built a very detailed model of the world. And normally I'm very wary about moving the robots close to obstacles, especially without some pretty robust perception. But we know exactly what the planner is going to do. We have sort of a very precise picture. And so we can use this approach as well. So if, I could talk for a long time about graph of convex sets, but I think the picture I'd like you all to come away with is this idea of imagine a probabilistic roadmap, but instead of little individual points, each of those points is actually sort of a large region where you're now you're not just deciding which vertices and edges in the roadmap you're moving through, but how you're moving through each vertex. Does that picture make sense?
Yep.
Yeah. So I always like just showing videos of the robot, but my advisor always tells me that numerical results are important too. So if we measure the path length with all of these methods, so for reference, the methods are TrajOpt is the trajectory optimizer without the parameterization, and then Atlas RRT and Atlas PRM are two sampling-based approaches using that piecewise linear approximation. And then the IK methods, we have TrajOpt with inverse kinematics, we have RRT with inverse kinematics, PRM with inverse kinematics, and GCS, graph of convex sets. And the main thing I want to point out, there's with the trajectory optimizers, at some point I couldn't get rid of all the collisions. So I've just tagged trajectories that collided with an asterisk. And the main thing I was going to say is the trajectory optimizers are sort of consistently coming up with the shortest paths. Sometimes the non-GCS trajectory optimizers are doing better, but that comes at the cost of bumping into obstacles and sort of not having any guarantees. If we look at planning time, this is where the picture gets really interesting. So obviously the probabilistic roadmap methods are the fastest, right? Because they just, all you have to do is find a path through the graph and boom, you've solved the planning problem. But aside from those, the graph of convex sets planner is extremely fast here, which is nice because like we've tried to take all of the work that we would be doing at planning time, and we did as much as we possibly could ahead of time. Just like with the PRM, you build a graph, you do the same thing with graph of convex sets. But let's compare the two RRT approaches. If we look at the Atlas approach, which is building the piecewise linear approximation, in these experiments, it's 3 to 4 times slower than the approach using inverse kinematics. Now, obviously, all these planning times are pretty long. A big part of that is that we wrote everything in Python, and we didn't spend a ton of time trying to optimize things. But there's a lot of tricks you can do to bring the planning times across the board down. And certainly, there are problems where I've run RRT. I can actually show you right now where I get plans in like 5 or 6 seconds. Here, I'll give you another one. Another little interactive demo. So, okay, planning started there. And it is done. And this is the plan it comes up with. So, I mean, these, it's not instantaneous, but we're getting these plans pretty quickly, I think. So, anyways, okay, back to the slides. So does anyone have any questions about that? Obviously, there are a million motion planning algorithms out there. We couldn't compare all of them. We tried to sort of get the most mainstream ones people know about. But like, if you're working on a project, or maybe you're doing an internship, you're working at a company and they have their own in-house motion planning algorithm, or they use a different one that's not listed here. You absolutely can use it with this approach, which I think is pretty nice.
So, so between the IKPRM and IKGCS, we see that the IKPRM take less time than the GCS. When would you want to use GCS as opposed to PRM?
That's a good question. So I think the paths that GCS comes up with are usually going to be a lot shorter than what a PRM comes up with, because the PRM, all it can do is move from sort of vertex to vertex in a straight line. It doesn't have sort of the built-in freedom to sort of shorten or optimize the paths. And there's definitely approaches out there like smoothing or path shortcutting. There's all sorts of tricks you can use to take the output path from a PRM or an RRT and try and make it look better. But I think to some extent, it's nice to be able to sort of solve the whole problem all at once in one shot.
Yep.
So that's what I would say. But I will say that GCS, there's also sort of, the setup time for GCS can be a lot more than a PRM.
Okay.
Because you have to get these collision-free sets in configuration space, and that's sort of a complicated question. Oh, and one other reason that GCS might be better than a PRM is that because the regions are, they're positive volume, right? They're expansive and they fill the space. You don't deal with the cursive dimensionality as bad as a PRM, right? With a PRM, you're going to need exponentially many samples as the dimension grows higher. So we've used GCS for like bimanual mobile manipulation robots with like 16, 17, 18 degrees of freedom. And GCS does a much better job. Like you can't even, for a PRM, you might spend hours and hours building a massive roadmap with like hundreds of thousands, millions, even tens of millions of nodes. And at that point, GCS will be faster and it'll still come up with better paths.
Got it.
So one other cool thing GCS can do in this domain in particular is, right now, we've always fixed the transformation of the end effector, right? We've always said that they're exactly this distance apart. But if we're doing a thing where we're like picking up heavy objects, they're going to be different shapes. We're going to grab them slightly differently each time. It doesn't help to have a perfect roadmap or a perfect graph of convex sets for exactly one grasp distance and one grasp transformation. But we can treat properties of the grasp transformation as additional degrees of freedom. So now, if we vary the grasp distance, now it's a 9-degree of freedom system where we're allowed to move the hands apart. And then here I'm just showing sort of like a random walk around one of those sets. And you can see right there, the hands just got wider. So, and then when we get to planning time, we just say, once you've grabbed it, we say, aha, we add this constraint. We say, we are now fixing the grasp distance. And in this case, yes, it's an equality constraint. You lose a degree of freedom, but it's really easy. You just say that, your parameterization might be θ1 through θ7, phi for the self motion, excuse me, and then d for the grasp distance. And planning and just saying that like, d is equal to 10 centimeters. That's not bad. We can deal with that. And that actually allows us to do, motion planning tasks where we're moving objects of different sizes. And that graph of convex sets that we made, we are now, we are using the same one for objects of different sizes. So you do get that sort of degree of flexibility that a probabilistic roadmap wouldn't. And of course, for the unconstrained motions, we were just using an RRT because it was quick and easy to implement. You can see here now we're going to grasp a larger object. So, while it's moving that to the shelf above it, maybe this is a good time for some more questions.
Questions? I think there is one. Yeah.
On the timing sheet, I think it was IK with trajectory optimization had collisions for top to middle and middle to bottom, but not bottom to top. I think that's right. Is there
Yeah. So this is sort of the frustrating thing with trajectory optimization. I have kind of a love-hate relationship with it. It's if you think about like an optimization landscape, it has a ton of local minima, and you need to like have a really good initial guess for it to find a good answer. Or sometimes it'll come up with a really bad answer, like it'll have a really long path. The most frustrating thing, though, is if I give it an initial guess that is collision free, it sometimes gets a little the algorithm behind the scenes will get a little too aggressive trying to shorten the path, and will sort of find its way to clipping into obstacles. It'll have collisions, and it'll get stuck, and it doesn't know how the iterative algorithm doesn't know how to like back itself up and avoid that, which is really frustrating. So I think there are people out there who get really good at trajectory optimization and sort of learn how to write really good problems that avoid these. Like at Boston Dynamics, for example, so much of what they do is trajectory optimization. And they have like these wizards who are just really, really good at writing out these problems in such a way that the algorithm doesn't get stuck and that it does well. I am not so skilled yet. I'm still learning. But yes, so that's why I think sampling-based planning is sort of a lot more reliable for a lot of things.
Yep.
Cool.
Any other questions? Nope.
All right. So I think that's the sort of the majority of the main content of the lecture. I have a couple of sort of fun bits here at the end that will be interesting, and then if we still have time, there's obviously Q&A, and then I can show like some other sides of things. But when I started out, I said that I want robots to run fast. I want them to run at their hardware limits. And those videos you saw were at real time, but we've all seen robots move faster than that. And I really want to, I really do want robots to run as fast as they possibly can. And we tried that. We started to run into a couple of issues. So this is a bit of an outtake from when we were recording videos for the paper, where I just cranked the speed all the way up. Watch the hands. You'll notice that they're not doing so great at following the trajectory they're supposed to. If I hadn't muted this video, you would have heard my co-author Seiji getting very scared because he's just off screen, rather close to that arm. And these are like big industrial arms. They're very strong, so it's a little scary when they don't do what you thought they were going to do. So it turns out that the issue here is actually the low-level controller, because what we're trying to do is we're going to give it a trajectory, and we try to follow it as precisely as possible. If you think about a PID controller where the P term is just not tuned high enough, it can't keep up. So this was like a real problem. We didn't have like an easy way to fix this immediately, and it was really hard to diagnose what was happening. At some point, we were running out of time. It was like I was in the lab till 10 p.m. every night before the paper deadline, and I said, okay, it's good enough. We'll just run the arms a bit slower. And I was explaining this to my friend Nicholas in the lab, and he was basically saying, that's funny. That shouldn't be an issue. I bet I can do better than that. And then we sort of didn't talk about it for a couple of months. And then like 6 months later, not quite, no, it was like 4 or 5 months later, he comes back to me. He's like, I've got a much better controller for you. So this is just an example of what the new controller looks like. And you'll look how fast we're moving. The hands are perfectly matching. And it turns out there were a couple things. It's not just a PID controller. He wrote some really special code for me that I don't fully understand yet, but I trust him that it won't, try to kill me. And in this case, we accidentally ran a piecewise linear trajectory instead of a smooth one. So you can see it's like starting and stopping. which is very dynamically and elegant, but the controller has no problems. And then, of course, I can run like nice smooth trajectories with it as well, and it looks like, you know, a lot more elegant, like something to actually be happy with. And credit where credit is due. I have an undergrad researcher, Shruti, working with me, who's been doing a great job coming with these trajectories. She's also done some cool stuff about like balancing how much work is going into each of the arms. Like if you think about it, with the controlled and subordinate arm, we're only trying to make paths short for the controlled arm. The subordinate arm might have to sort of work arbitrarily hard. And she's been doing some great work on balancing the amount of work that each of the arms have to do. And so yeah, so this is our paper is titled "Constrained by Manual Planning with Analytic Inverse Kinematics." As Karthik said, we'll be presenting it next month. But if you look up the paper, I tried to avoid getting too deep into the math. I wanted to just give you guys some of the background and the ideas. But if you have any questions about the paper, you should always feel free to send me an email. I'm always happy to talk about this stuff. But I'm really grateful to my co-authors for their help on this. This was a really fun project for us. Karthik, does your lecture end at 3:15, or did you want to make sure to have time for Q&A? Because I have a couple of extra things we can talk about if there's time.
So yeah, we have like 10 minutes time.
Okay. So I think, okay, in that case, why don't I go to Q&A? I think the last two subjects I had for sort of extra stuff were maybe would need a little more than 10 minutes. So
before we take questions, let's thank Tommy.
Thank you so much for having me here to give a lecture. It's really great to talk about this stuff with you all.
The pleasure is mine. Any questions for Tommy on the lecture? Yes.
So for a lot of the examples we're seeing with the bimanual planning, the two Kuka arms, it has a white sheet in the background. Is that just to increase invisibility, or is it for specific like tracking purposes?
Karthik probably knows the answer to this one. So we're not actually doing any perception here. All of the sensing information is coming from the encoders on the robot arms. So each of the joints is measuring its current state, its velocity, the torque, and the low-level controller is using that feedback in order to follow a trajectory. No, the sheet is because our lab is a mess, and it looks very unprofessional when there's just like tons of robot parts and other things strewn around behind it. It's like when you see like videos with papers, usually people try to clean things up or make things look professional, and we didn't have time. But yeah, for some other projects we're looking at, we will actually be using it for that reason. We're doing some like reactive manipulation where you have to avoid dodgeballs and stuff that you throw at the robots. And our plan for perception, instead of, if we had time, we would write a neural network. We would use mask RCNN and write a full perception pipeline, or we could just have red dodgeballs and a white background and a camera. So yeah, so we will be trying something just like that.
So I had a question, like in the sense more on the perception side, which I know you're not working on that, but like, so the shelf that you showed, just so that the students understand here, how did you model the shelf and its location with respect to the arms?
So in our case, like I said, we weren't thinking about the perception. We did some stuff. We basically built up a simulated model of the world where we had the two robot arms and we had a model of the shelf. It's SD format, if you're familiar, along with the table. We fixed the transforms for everything, and then the planner was taking that into account when it was doing collision checking and stuff. If we wanted to throw this into an unknown environment, that's where things get a little bit harder. In those cases, a lot of what I've seen has done stuff with like you'd have a wrist-mounted camera on the robot. And I think that's sort of like a very nice embodiment for sort of when you're doing manipulation, you don't really care what the arm behind you is doing, you just care about the hand. But I think in environments with lots of obstacles, it would be, for like a humanoid robot, we can sort of look at our hands and watch for collision avoidance. So I think once you throw perception into the mix, it definitely becomes a harder problem. But whatever you would do with sort of integrated perception and motion planning in novel environments for unconstrained planning, this would, like I said, any planning algorithm will make it work. So,
So I'm just curious. You probably have the solution for this. So let's say I'm grabbing a salad bowl or something.
Yeah.
Like this.
Mhm.
Which means if I do grasp planning, it gives me a bunch of grasp poses on the concave object,
Mhm.
and then I would do IK to get and grab that, and
Yeah.
then let's say we use your system. Have you done stress testing on the 6 DOF configurations that you'll have to match?
Ooh, that's interesting. So that's not something we thought about a ton. Because we're using arms that have that 7th degree of freedom, usually we don't have too much trouble with like non-reachable configurations, right? I mean, these arms are designed to have relatively similar workspaces to the human arm. I will say that our choice of parameterization with like a controlled arm and subordinate arm might feel a little unnatural for those tasks. It might feel more natural to think of like the end effector pose of each hand. Like you specify the shared end effector pose, and then you have a redundancy parameter for each one. It's like you use self motion for the left arm, self motion for the right arm, and then 6 DOF end effector pose. And we had thought about that. The main challenge with that is, so just like there was the continuous self motion, how there's up elbow and down elbow. With one arm, with a 7-DOF arm like the EWA, there are 8 choices. There are 8 possibilities. So if you have 2 EWAs, then that's 64. And so the side effect is you're sort of cutting your configuration space up into smaller and smaller pieces. And that plus, the set of orientations being hard to plan over in general was the reason we wanted this. So I think that's gonna, whether you use this approach or another approach, it's really gonna come down to what kind of workspace your arms have.
There's one more. Yep.
So using the system that you've been showing us, would incorporating something like grip adjustment partway through, like your given bimanual path planning, be something that's like easy and realistic, or something that's just like a trivial problem, or something that's more complex?
So I can think of like sort of silly hacks that would do that in some way, but I think the interesting question is really on the perception side. How do you realize that your grasp has slipped? How do you identify that you no longer have the appropriate hold on the object? Are you looking at the grippers and the forces that they're reading? Maybe when the object has changed state a little bit, suddenly you're reading torques in your joints as a result of like the constraint not matching up right. I think it's interesting to ask, like, how do we identify whether it's constraint planning or just general manipulation that like the object has slipped in our grasp? But I mean, hopefully in those cases, if it's not a super heavy object, you could sort of hold with one arm and just move the other arm a little bit to fix it. Or in the worst case, put it down, regrasp, and pick it up. If it's a heavy object or something that you can't like set it down, that seems like a really hard problem. Like if we have dexterous hands, maybe you need to do something where like you do some in-hand reorientation or manipulation to fix your grasp. But that's like, I think that's sort of beyond the bleeding edge of what we can do right now.
Cool. I think we're close to the end of the lecture. Thank you so much, Tommy, again. Thanks for doing this, and have a nice trip to Japan.
Thank you. All right. Thank you so much, everybody.